pause karo. In the meantime, the session will continue. In the meantime, if any question arise, then we will take the questions as required. Okay, sir.
Okay. Yeah. Okay.
Okay, sir. So should we accept the participants in the webinar?
Yeah. Yes.
Okay. Thank you, sir. Thank you.
Yeah. Hello.
Yes, sir. We will starting our today's webinar. So we, on behalf of Chaibasa Engineering College, welcome you all to this this virtual lab webinar. We have eminent professors with us today, and we have with me Mrs. Biyash Bhadro, Madam, and Mr. Debojyoti Sarkar and Mr. Bapaditya Jana. He is the HOD of Computer Science and Engineering, Chaibasa Engineering College. They will be assisting us throughout this webinar, and I'd like to request my co-host, Mrs. Biyash Bhadro, Madam, to continue the session. Thank you.
Thank you, sir. Good morning and a very warm welcome to everyone. Our Honorable Director, Sir, Dr. Sudipta Chakraborty, our respected Principal, Sir, Dr. Ranjit Roy, and all my respected fellow colleagues and dear students. Thank you for joining us for today's webinar. My name is Bias Bhadro and I am the host for today's webinar organized by Chaibasa Engineering College. Today, we are presenting the TEQIP-III sponsored national webinar on a digital initiative for the future, that is virtual laboratory. It will be presented by Dr. Chittaranjan Mondal, eminent professor from IIT Kharagpur. Just a little housekeeping before we get started. If you have any questions during the presentation, you kindly type them in the chat box in your Zoom control panel. I'll bring them up during the presentation, and we will also have some time for the questions at the end. Now, without further ado, we will turn the time over to our presenter today, that is Dr. Chittaranjan Mondal, sir. He is an eminent professor from Computer Science and Engineering Department, IIT Kharagpur. His research areas include VLSI CAD, networking, formal verification. He has also received various prestigious awards and honors. He has also written various text and reference books, namely Nanoscale CMOS Analog Circuits, Verification and Synthesis of Digital Circuits. He has pioneered various projects so far, one of the most important one being the project title under MHRD as Virtual Lab for Computer Organization and Architecture. He is the principal investigator in this MHRD sponsored project. Thank you so much for letting me introduce sir to all of you. Now I would like to hand over the session to Dr. Chittaranjan Mondal, sir. Sir, over to you.
Yeah, thank you. Let me just give a little bit of background. So this project started many years back under the auspices of MHRD when they initiated the development of several virtual labs. So many institutions across the country, mostly IITs though, also I know IIIT Hyderabad and a few other places were involved in the development of various virtual laboratories. All right. So this activity is presently being coordinated from IIT Delhi. So in the initial phase, many virtual laboratories were developed, and this is one of those virtual laboratories to assist with experiments in logic design and computer organization. Now, as you might expect, that this is a challenging activity. So unlike many of the other virtual labs where you see dedicated experiments, for example, I am also associated with the development of the basic electronics lab. So there, for is that lab already, was that lab covered yesterday, or is it scheduled for today afternoon? Hello? Hello?
Yes, sir.
Yeah, that basic electronics lab, was that,
Yes, sir. Covered yesterday, sir.
oh, okay, so they might know about it. So in the basic electronics lab, you have individual experiments. For example, the measurement of resistance and many other gain of amplifiers and all that. So many experiments are there, but the experiments are relatively simple, where you just change a voltage or current or some signal or a component value, and then you can just take the measurements. But over here, actually everything is flexible. That means you can design for logic design and computer architecture and organization, you can design any circuit as you like, and you have to see whether that works or not. So for that purpose, I mean, we do have a list of experiments. If you have looked at the page for this laboratory, you would have seen a list of experiments, but all of those experiments require essentially a logic simulator, okay? And that too at the, what do you call, the register transfer level. So we simulate at a logical level. We do not simulate circuits as such. We simulate at a logical level, at the level of gates and registers. Registers are also implemented as gates only. So this requires so the supporting mechanism is more complex. So at that time, at the time when this lab was developed, we decided to develop it as a Java applet. In fact, at that time, Java applets were very popular. But in course of time, things have changed. In fact, nowadays, Java applets are not used much. Nowadays, JavaScript has in fact become absolutely mainstream. So at that time, the situation was different. In fact, if we had known that in the future, Java applets would go out of use and the main vehicle would have been JavaScript, then we could have developed the lab in JavaScript, and that would have been more convenient also for everyone. I mean, we might still do that, but so that is the reason why this lab is different from the other labs. That is, you have to you have to save a Java jar file and then run that file for this lab. Now, so that is just the background. So Aditya, can you start the simulator and bring it up on the screen so that I can
Yes,
just introduce them to the basic layout of the interface. Yeah. Okay.
Yes, sir, it was
So,
on.
all right. So now this is supposed to be a hands-on workshop. So I would just ask the participants also to start the simulator on their own computers. So Bias, can I just ask you, are the participants also using the simulator? Have they started the simulator on their computers? Hello? Hello? Yeah, hello. Is there anyone on Chaibasa Engineering College
Yeah,
side?
yeah, yeah. We are there. We are there.
Yeah, so I am asking on your side also, have you got the simulator running on your computers?
Yeah, just let me confirm with the departmental representative. Just 1 minute.
Yeah, so you should have a screen like a screen like what is displayed here. You should have a similar screen.
Yeah, okay, okay. Just for all the participants, we have shared the link of the this software earlier with all the participants. So they are using this kind of screen.
Okay, so I hope they have also started the simulator, right?
Yeah.
Yes, sir. Yes.
Okay, so over here, just I will give you the idea. So it is meant to be used almost like a breadboard. So I'm sure, yeah. So please, let it be interactive. So I'll ask a few questions. You please get back. So this is uh, uh, supposed to give you the almost the feel of developing with a bread on a breadboard. Okay, so you have a matrix over here, and what you do is on a breadboard, you place components. Maybe, I mean, you can place transistors, resistors, and all that. But as I indicated some time back, that we'll be working at the gate level. So we'll assume that we are working with gates, as if those gates are present inside chips. All right. So with dual inline packaging. So the idea is that, I mean, the feel of the interface is meant to be that you can place those chips on this working area, and you can also connect the terminals. All right. Now we do not bother about the voltage supply. We assume that the voltage supply is available. So we just connect the other pins, the input and output terminals, as required. So now, so if we just think of a very simple experiment, let us say you have an AND gate, you want to test an AND gate, and so how can you test an AND gate? The way you can do it is you first place the AND gate on this work area, and you apply two switches through which you can apply the inputs to the terminals. Okay, you can apply the inputs to the terminals, and then you also have observation. The observation mechanism is an LED, so you can connect just a LED display at the output. So you can provide uh, uh, suitable inputs, and you can observe the output. So I think Aditya is doing it for you. So he has placed an AND gate. No, he has placed, yeah, that red thing is an AND gate. He has placed, yeah, he is placing it. Okay, he has placed an AND gate now. So now he will connect the inputs. So those aquamarine or bluish circles, those are the inputs. And he will connect those to the inputs of the AND gate. And the output he will connect to that display. All right. So this is what he has done. All right. So now let me just explain a few things. So to the right, you can see a palette, right? You can see a palette. So in the palette you have various components. So right now, what is visible, you can see a number of gates: OR gate, AND gate, NOT gate. So you have a number of gates. Then so you have a number of gates. Then you have other tools also. So below that you have a bit display. Then you have a bit switch. You have a digital display. So a bit display will display the 0 and or 1, and a digital display will display numbers. So for example, if you have a 4-bit code, then so as you might have noticed, right now he has placed 2 bit switches and 1 bit display, right? Now there are other inputs also. For example, a clock pulse. So a clock pulse is required when you're working with sequential circuits. That's when you also need a clock pulse. Now there are, if you look at the upper part, right hand upper part, you'll find that there are a number of tools over there. So you have a selection tool. The selection tool is required. For example, if you wish to move a component or delete a component, so before you do anything, you'll have to select the component. So for that, you'll have to enable the selection tool. Then he showed you that the bit switches. He showed you how to the connection of the bit switches to the input of the gate. So that was done using the connection tool. Now before you make any connection, you got to enable the connection tool. So once the connection tool is enabled, you can make connections. Now there are other tools also, clone tools. So clone tool, so if you like to duplicate a part of the circuit, so you can select a part of the circuit and just clone it. That is useful when you are making a bigger circuit. Then there are other connectors. For example, sometimes it may be desirable to connect a number of outputs through a bus. So for that you have a bus connector. Those things are a little more advanced. So we can go into those later. So these are various tools. All right, now down there you have, so you have right now you have seen some relatively simple components like gates. Now of course this lab is for computer architecture and organization. So when you're doing some experiment on computer organization, then it starts them to do everything in terms of gates alone. I mean, ultimately those are done in terms of gates, but when you're designing, so there are other components as well. So you can so you have sequential circuits, basically flip-flops. You have other
Sir,
components. Yes.
sorry
Yes.
to interrupt you, sir. There is a participant. He is asking you, sir, can you please show once again how these connections are made using the connection tool?
Yes, he will show it once again. I'm just
Yes.
let me just he had made the connection. So if you just look at the circuit, he will show it again. But you can see that the bit switch is connected by those lines to the inputs of the So he has in fact deleted those. So he is showing it once again. He has enabled the connection tool. Now he is making the connection. So you can see how it's making. So it is just drag and drop, nothing more. Just drag and drop. Okay. So is that clear? All right. Now let me just tell you that this connections, these are a bit intelligent. There is a little bit of intelligence also in this. So so you know that connecting two outputs is problematic. So certain checks are made. You will find that if you use this tool, it's not if you try to connect to outputs, it will stop you. So now, as I was saying that if you're doing a more complicated experiment, then doing everything in terms of gates may be a bit challenging. So for that, other components are also provided, such as adders. So you can just show the so you can see some various kinds of adders: half adder, full adder, ripple carry, 4-bit adder. So various kinds of adders are shown. Then you can just show the palette for sequential circuits. So number of sequential components are also shown. So you have got basic flip-flops. Then you have got more complicated sequential circuits also. For example, a Booth's multiplier, data path, shift register. So you can just see various kinds of shift registers. Then you have got other components also, like 2 to 4 decoder, multiplexer, RAM cell, ALU, IC memory, associative cache. So in fact, this tool is good for doing a wide range of experiments. In fact, we had even done CPU design with this, a simple CPU design, of course, but we had done uh, we had designed a simple CPU also with this. So of course, that is quite a lot of things can be done. So today we will not be covering so much. We will be only covering some basic capabilities of the tool. So as you can see, for computer design, you have got CPU, memory, and very interesting aspect is that we have got some support for a control unit design. Okay, so you know that when you design a sequential circuit, you know, uh, if say a multiplier or a divider. So you have a data path, and that data path is controlled by a controller. So we have facilities here to specify or such a controller in an abstract way. Of course, you can design the controller using a finite state machine, but that is cumbersome. So for designing the controller, we have we have some facilities for designing a controller. Of course, everything we can't cover today. I mean, we have a plan to visit Chaibasa Engineering College sometime in the future when the situation is better. So at that time, we can look at more advanced features of this tool. So today we'll restrict ourselves to only some basic features. All right, I think Aditya, I think what you can do is you can just simulate this circuit and show them. So this bit switch, you can either give you a 1 or a 0. So if you click on the bit switch, it toggles from a 0 to 1. All right. So I would encourage all of you, I mean all the participants also, to do this exercise. So please draw this in a similar circuit. Okay, Aditya, I think so that they can follow you, because most of them are actually following individually. They may not be in a lab together. Though in the lab 2-3 people might be there, but most of them may be doing it individually. So you cleared the screen, and in a very stepwise manner you show them how it can be done. And other participants, I would ask you to follow his instructions and repeat the procedure on your own computer so that you can also do the experiment. So the first experiment could be to test a gate. I mean, you could just test the AND gate first. Then there are other gates. You can test those gates also, one or two of those. Then you can go over to another experiment. So Aditya, can you just do that? Can
Yeah,
you
oh,
just,
sir.
yeah. So just clear the and start from the beginning. And other participants, please follow carefully what he is doing and repeat the same on your own computers. Okay. So you take over now. I'll keep quiet. All right.
Okay, sir.
Yeah.
Yeah. Yeah, simply from the logic gates panel, you can just click on the gate and click on the canvas or the grid here. To add inputs and outputs, go for input output palette and just click on bit switch and click on the grid. So it's a 2-input NAND gate. So we need to add 2 bit switches, and to see the result, we'll add a bit display. It shows, this bit display shows only 0 or 1. And these are the bit switches. It changes its values from 0 to 1 on double click, like this. So we have a NAND gate, 2-input NAND gate, and 2 bit switches and an LED display. Not an, sorry, it's a bit display. So we have our input components, our NAND gate, and a bit display. So now we need to connect. In the right hand side panel, go for the connection tool, click on it to select this connection tool, and come to the grid, click on the bit switch and click on the pin where which you want to give the input. Do the same for the second bit switch also and click on the output pin to the bit display. So now once we are done with the connections, go back and select the selection tool, and here you can adjust your components according to your view. You can zoom in or zoom out using these two zoom in, zoom out options on the screen. So once now the entire circuit was ready to simulate. We have a NAND gate with 2 bit switches and a bit display. So to simulate this, you need to click on the simulate button here. So once it was pressed, you can observe that the bit display output was changed. If 0 and 1 are the inputs for a NAND gate, you will get output was 1. You can, like this, you can verify the different combinations of inputs and you can observe the outputs. In this way, just basic gates can be simulated. The same way you can test the other gates also on your own later onwards. If you have any questions till now, you can just post in the chat box so I can answer. This is for the AND gate. Yeah, Sony is asking about the simulator is free to download. Yes, the simulator is free for all. You can download from our web page. Any more questions? Just a minute, I'll show the web page also.
Hello, Aditya.
Yeah,
One,
this is the
yes, one
this is the
show the
main
web
web page of Virtual Labs IIT Kharagpur. And if you go to the Virtual Labs IIT KGP tab, under that, if you press Computer Science, you will get this lab, Computer Organization Architecture Lab. If you press on this, if you go to this page, in here, you will get the software tab. We'll have a different set of experiments. We'll have a different set of experiments listed here and a software tab. And in this, you can find your software. You can download here and you can run on questions. Just a minute. Yeah, somehow some students some people said that it was done. So it is a simulator location. You can download at any time. And we'll get back to the simulator. And if you want to do, we have some practical. We have we have 4 experiments here. You can download and you can run on your own. These are ready to use experiments just for the workshop kind of thing. We already developed and we placed in the workshop page under this page. I'll show how to run some other experiments from this page. You can download the first and the last 2 experiments. You can use. I'll show a 3 set of examples from this workshop page. So if you want to clear the screen, you just use your clear button here, clear screen button. You can clear it. Now we'll see an example of half adder logic using gates. This is an half adder logic design using gates. It has 2 inputs, A and B, and the sum we will calculate as A XOR B. We used here as an XOR gate, and the carry is A into B.
Yeah,
So here,
Aditya,
yes, sir.
I'll just add a little bit. Okay.
Yes, sir.
I mean, when you're working with Boolean logic, you don't say into, you say and. All right. So it is
Yes,
A
sir.
and B. All right. Now,
A and B, yeah.
over here, you might have observed that there are some more features. So in the earlier circuit, in the earlier example, you have just seen the gate, the bit switches, and the bit displays. So here you notice something more, right? You notice labels, A, B, sum, carry. So this tool has the facility to add labels also. So Aditya,
Yes, sir.
you have opened this. You can do one thing. You can clear your screen. You can just go back to the previous simple experiment, take any gate, and just show them how to add labels. Because
Okay, sir.
labels are very convenient. Because without labels, you won't know how to, you'll forget about which terminal is for what. So just
Sure,
clear
sir.
the screen. You can come back to this later. Just clear the screen, just draw a simple circuit and just show them how to add labels also.
You can use label option here. You simply drag and drop the label, select this, and click on, select this label which you have placed on the canvas and go to the left panel. You can see set labels and set names. So I want to set a label name of this to A. So I did this and my input one was labeled as name A. Like the same way, I want to add label name to the second input. Simply click on the label and go to the left column, left side, and place your label name here and just label it. So now my two inputs are labeled as A and B. I need to label my output. So I'll just place a label aside of the output and I'll just make it as some output. So my output was named as output. In this way, you can label your components. If I want to label the NAND gate also, I can. You can try on your own in your laptops and you can see the labeling part. And just let me know once you are done in the chat box.
Yeah, so that way, whenever you see a new feature, just explain how to use that feature also. Okay.
Yeah, sure.
All right. Okay. All right.
Sir, few participants are saying done, sir.
Okay. Then we'll move on to that half-fired experiment.
No, I think there is no need to rush. Let all the participants just give a little bit of time. You can give them a minute or so, half a minute, so that they can complete this part. And then, of course, you can go back to that half adder. Okay.
Yeah, sure, sir. Already few people was said that it was working fine and done, sir.
Yeah, all right. Okay.
Then we'll move on to that next one. Yes. And kindly note that if you are saving this, it will save these files as a .logic files. It will save it as a .logic files. Note this point. If you are saving anything.
Yeah, Aditya, I think
Yes,
don't talk about saving just now. You can design a small circuit and then show them how it is to be saved. All right.
Okay, sir.
Yeah. So first you can just demonstrate. You can So basically, just tell them that So the designs that you make. So this tool supports modular design. Okay, it supports modular design. So the components that you design can be saved, as you have already seen, those HA.logic and all those things. So those components are designed in this tool itself. So you can design your own components and save those, and you can design bigger circuits using those components. So that is a useful feature. So this tool has support for modular design. So he is essentially using those saved modules. All right. Okay. Yeah. So yeah. So carry on. Carry on.
Yes.
Sir, sorry to interrupt. Some
Yeah.
faculty is asking, please show one more time how you implement half adder circuit.
No.
Yeah. Okay.
Hello. No.
Yes, sir.
No. Let me just say, he is currently not implementing half-adder circuit. Of course, it is easy to implement. You can see the implementation is very simple. It involves just 2 gates. But right now, what he showed you is he is reusing an existing implementation. All right. So right now he has just loaded he has just loaded a saved circuit. He has not designed the half adder right now. He had designed it before and saved it. So right now he has just loaded the saved design. You understand this, I hope. So after some time you can also show them how to design the half adder and save it. All right. Yeah, is that okay, Aditya?
Yes, sir. Yes, sir.
Yeah, okay.
Yeah. Generally, the half adder, as we discussed earlier, it has a XOR gate which was calculates the sum of A XOR B, and will generally have AND gate to find out whether there is a carry or not for A and B. So if I have 2 inputs, both are ones, then I'll just press on simulate to check. If we add two binary digits, 2 binary ones, you will get sum as 0 and carry as 1. So as sir said, we can save this half adder circuit as an component also. And for example, there are half adder IC circuit also here. IC was there. You can click on here and click on this. As you are seeing, this entire one was gate level half adder circuit. It is an IC level half adder circuit. If you want to know the pin configuration of this, just click on the half adder and click on this icon, which gives the pin configuration. So this is the half adder. As you all know, to see the calculate the pins of an IC from this notch to 1, 2, 3, 4, and 5, 6, 7, and 8. So
Yeah,
in this in
Aditya.
pin configuration, yes sir.
Yeah. Oh, okay. I'm just. Okay. You finish. You explain this. After that, I'll tell. Finish your
Yes,
explanation. After
yes,
that, I'll
yes.
tell.
And in this pin configuration, you can observe that 5 and 8 are the inputs, like as A and B, and sum and carry are 4th and 1st pins. Sum and carry are 4th and 1st pins. So to use the IC level also, you need to use your bit switches and 2 bit displays. We have our inputs as 5 and 8. So we'll connect 8th pin and 5th pin or as our inputs, and outputs for carry is 1st pin and sum is 4th pin. So now we connected our circuit as is. We'll just label them as 4th pin is sum and 1st pin is carry. And our inputs A and Sorry, if I just disconnected. Just a minute. Yeah. So have a gate level design and then IC level design also with the same half adder, and we can see the result. In this way, you can design your digital logic circuits by using is the gate level, yeah, IC level also with this simulator. Sir, over to you.
Yeah, Aditya, I would say that don't use the term IC level, just a module. It's a module. You can say that you're using a half adder module. All right.
Yes, sir.
Yeah. So yeah, it has the look of a means the visual appearance is that of an IC chip. That is true, but just think of it as a module. All right. Yeah. So I would like to give you an exercise. All of you, please make a note of it. See, you must be familiar with Aditya. You can note down. You can note down on a piece of paper and post it. So just note down as I say.
Yes.
So you are familiar with the design of a block carry lookup adder, right? Yeah. Are you? Yeah. The participants. Are you familiar with the design of a block carry lookup adder? Hello. Hello.
Yes, sir.
Yeah. Are you? See, you must be familiar with the design of ripple carry adders and block carry lookup adders, right?
Yes, sir.
So in a ripple carry adder, the ripple the carry ripples through the stages sequentially. So the the time taken is linear. Now with block carry lookup adder, the advantage is that it is the carry time is reduced significantly. It is logarithmic in the number of stages. The you know using the block carry lookup principle. So using that same principle, you can also design a comparator. So let us consider a simple comparator. Less than, say, you have got two n-bit numbers. Let us say A and B. Okay, so this is the problem statement. You're given two n-bit numbers A and B, and you are required to design a less than comparator. You just want to check that A is less than B. So how can you do it? So you can do it in a ripple carry manner. You can, of course, define the condition when A will be less than B. So can you write down? So when will A be less than B? If the most significant bit of A is 0 and the most significant bit of B is 1, then of course you can say that A is less than B. If now if A is not greater than B, that is when A is less than B. If that is not the case, then the result will be so if B is not if A is not greater than B, then the result will be determined by the result of comparison of the remaining bits. All right. So based on this, you can design you can define the a way to compare. You can define the operation of a comparator for A and B. So this way you can easily define a sequential, I won't say sequential, but a ripple carry comparator. So if it is not decided by the most significant bit, it may be decided by the the bits before that, or if it is not decided by those, then again the bits before that. So in the worst case, it can go all the way to the least significant bit. All right. So you can easily design a ripple carry comparator, less than comparator. Now this, of course, just like a ripple carry adder, this ripple carry less than comparator, it's there can be rippling, so the time will be linear in the number of bits. Now this can be made more efficient using the block, similar to the block carry lookahead principle. You can have a block comparator, okay, block lookahead comparator. So you can using a very similar principle, you can design that, and those will all be done using those modules. So you can design those modules on paper and save them as those logic files, and then you can use those and build a comparator using those in a modular form. You can build a comparator. So I would give this as an exercise to you, and I would so let the presentation by Aditya go on. So I would ask you to from the college, I would ask you to submit this one design only from any one of you. Then we'll know that the workshop is successful. All right. So from your college, you should submit the design of a look ahead, block carry look ahead less than comparator. So have you understood the question? Hello?
Yes, sir.
You have understood so this is your exercise. So from the entire college, you can collaborate among yourselves. There is no issue there. But from the entire college, say by the end of the day, or even tomorrow, if you send us those, so you can design, you can make a modular design, and you can save this in your you can do the you can do the labeling and all that. You can build the modular circuits, do the labeling, and you can save those as logic files. So Aditya will tell you how to do that. Say for a half adder, he will show you how. He has now showed you how to open a saved file. He will also tell you how to create the design and save it as a module. That also he will show. So then you can take it as an exercise and design such a block uh, look ahead comparator, and from your college just send us the set of modules, one circuit, a modular circuit for the block look ahead comparator. All right, so that is
Okay.
your exercise. All right,
Okay.
so, yeah, please carry on with your presentation. Yeah.
Yes, sir. Thank you. Yeah, as of now, we saw on the gate level and then just module level integration to simulate. I'll show a small example of a sequential circuits to design a shift register. You can find, as I showed in that web page. Yes,
Aditya,
sir.
you go to the sequential circuits a little later. See, you have
Okay, sir.
explained the half adder. Now, using the half adder, how you can make a full adder. Then you just show them the design of the ripple carry adder. So just show them those designs. After that, you can go to the sequential circuit. Okay.
Okay, sir.
All right. Yeah. Yeah. Carry on. Carry on.
Yes, sir.
No, Aditya, just you're skipping one stage. See, what you show them, you show them how to design a full adder using the saved half adders. All right,
Okay, sir.
how to design a full adder using, so that way they will understand how to do the modular design. Okay.
Okay, sir.
Yeah.
Okay.
Then you can go over to the other.
Okay, sir. Yeah, now we will see how to design a full adder from two half adders. We'll just use a modules of two half adders. And as we know, the pins are input pins 5 and 8, and the outputs are 4 and sum and carry. So for a full adder, we need one carry input and two inputs, and outputs are sum and carry, which are end of it. OR of the carries, and sum is the sum of the carry inputs and the input. So now we'll take two inputs and one carry input. We'll just label it for our convenience. So I labeled my three inputs as A, B, and a carry. and my outputs. Now, to make a full adder, we have two half adders now, and our inputs are taken as carry input and A and B. Now we need to connect two half adders to get the final sum input, sum and carry output of the full adder. To get the carry of it, we need to use OR gate for the carries of it. My inputs are 5 and 8 and 8. So here my sum will be gone to an output and two carries, sum of the carry, and the final sum is the sum. So in this way, we designed a full adder using two half adders. For example, if my inputs are, if I have a carry input 0 and if my inputs are A and B, I'll get the carry is 1 and sum is 0. If I have a carry input 1 and I had A and B are the inputs, then we'll get sum is 1 and the carry is 1, because here we'll take an so here we can design our full adder circuit using two half adder modules. If we have any queries regarding this, you can post in the chat box. I think I have two questions from Sujata Basu, and they are asking that how can we move from one figure to another. See, if you want to move any component or any module, you need to select the entire zone and you can click on it and you can drag. And can we remove the extra connections? It is unnecessary. Yes, you can. For example, if I have a connection like this, if I have this connection as I feel that it extra, then select the selection tool, select that connection and just press on delete. It will delete it. If you want, you can connect it back again. The unnecessary connections you can remove, and there is another option to route your connections like this. It will automatically adjust your space of the connections between the components also using this change connection type. So if you have any questions, you can drop in the chat box. Please try on yourselves so that you will get a clarity on how to do this. Someone said it has been implemented. Yes, good. We'll just give some another 2 more minutes to let the others also implement with this. I hope everyone done this. Can we move on to the next?
Yes, sir, you can move.
Okay, thank you. So now we will see how a ripple carry adder can be implemented using 3 full adders and then half adder. Meanwhile, I will show how to save it. Here's a logic. Just go in the top left corner. You can observe a save button here and press on that save button. Enter your name and your roll number and simply save at your whatever you will give a name. Now it was saved as a .logic file. You can, once it was saved, you can see your details here. For example, since I saved with my name and my roll number, if you click on show user ID, you will get your user identification here. That means I saved with my name Aditya and my some random roll number I given, my roll number. Like this, whenever you open your logic file, you will get that details will be saved for permanent. For example, I am just clearing my screen. So the screen was cleared. Now I'm opening my saved file. So I reopened my saved file, and if you click on show user ID, this ID will be reserved. Your name and your number will be preserved here for until unless it will be deleted. You can't delete it also as of now. It is permanent. So now we will go for the triple carry adder. As of now, you have seen the implementation of a full adder from 2 half adders. Now we'll implement 3 half a ripple carry adder of using 3 full adders and a half adder. This experiment you can see in the Virtual Labs website also. I'll just show that. Yes. In the experiments, we have a different set of experiments covering. In this ripple carry adder also you can go. Here you can have a circuit design and how to do it and how to connect it. Also we have a sample input sample design, and the label was also there. So I'm going to demonstrate this experiment only. So it is the ripple carry adder has 4 inputs: A1, B1, A2, B2, A3, B3, and the carry input. So these 4 full adder inputs are having 4 sets of like this. A3 like this. A0, B0, A2, A0 to A3, and B0 to B3, 2 4-bit combinations we are now going to add. So it is a half adder module and 3 full adder modules. We are seeing the output in final output in a digital display. In this digital display, you will get the decimal values. This is the 4-bit decimal values and a final carry. Let me label it. Just a minute.
Hello, Aditya.
Yeah. It is. Just a minute.
One question is there. If connection is wrong, how can it be removed?
Sorry.
If some connection is wrong connection is given, how can I
Just
remove?
click on the connection and just press delete on your system.
Just show it.
Yeah. For example, if I feel that example, I will show. If I feel that this connection is wrong, just click on the connection and press delete. Delete in your laptop keypad or so. If you want to change from 0 to 1, just click on the bit switch and double click on it. If you double click on the bit switch, it will change the value from 0 to 1 and 1 to 0. So this is we are adding a 4-bit to 4-bit values A and B, and using a ripple carry adder, you are having three full adders and a half adder. Here, the half adder will have 2 inputs and one carry and a sum, and full adder will have 3 inputs. 3 inputs in the sense, one is carry, previous carry, and 2 new inputs. So we'll connect this our ripple carry adder circuit like this. Now we'll add. So I'm adding 8, that means 1,000, and for example, I'm just deviating that. The upper line was A0, A1, A2, and A3. The lower line was B0, B3, B0, B1, B2, and B3. So we have 2 inputs A and B, and we're adding through the ripple carry adder, and the output was this. For example, if I'm adding F and F, that means since you are using a digital display here, it will show the decimal number to the base 10. These are the binary inputs. So I'll get a carry of 1, that means we are adding F plus F. The carry is 1 and the sum is 14. So you are adding F 15 plus 0. So the sum is 0 and the carry is sum is 15 and the carry is 0. So try this on your PCs, this circuit, and let me know. We'll give around 5 minutes time for you all to implement this. Yeah, someone posted as one person has done. We'll wait for some more, the others too.
Hello, Aditya.
Yeah,
One question is there.
yeah.
Check the chat
checking.
box.
See, to show the 14 in the digital display, you need to use 3 ones and a 0. It's a binary format, 4-digit binary format. It was shown on the screen. If you see this, 3 ones and a 0, you will see this. Make sure that your digital display is from right to left. LSB to MSB is from right to left. I hope everyone is trying. If done, let me know. We'll just go an example. We see an example of sequential circuit. Can we move on to the next?
Yes, sir. Yes, sir. You can move.
Yeah. Yes. You are seeing on your screens a master slave D flip flop based shift register. It's a right shift register. We have 4 master slave D flip flops with this pin configuration. Yes, the D input is 5 and clock input is 8, and Q and Q dash are 4 and 1 in 4 and 1 outputs. So here we have an extra component called clock. So for every clock pulse, this will shift one bit from left to right. Initially, all the inputs and outputs are reset to 0. Now my input was 1. So to start the clock pulse, you need to click on clock and place start clock. So the clock will toggle from 0 to 1, and you can see the 1 is shifting from left to right. If you want to change the input bits, just double click on the binary bit, and to run the clock, click on the clock. So now you can see the 0 is shifting. And now if you want to see the graph also, you can use this option, show waveform button on the top. So you will get a waveform like this. My binary input value was 0 and 1 initially. This is the clock pulse, and these are the bit displays output, which you are seeing here. You are seeing here, these are the bit displays. And you can see a graph like this also. For every clock, for example, I'm just making my input to 1, and my clock is running, and you can see. Now I made it. Oh, sorry. I'm able to share the screen. So this is the clock. Here it is a bit switch, and this is the clock input, and these are the bit displays outputs, one by one. So in this way, you can see your waveforms also if you are using a clock pulse. To stop the clock, stop the clock. Yes. There is a question from Subham regarding please show from first onwards for some more time. I'm just re-explaining the experiment. Here, this circuit has 4 master slave D flip-flops. You can get it from the sequential circuits. Here it is there. Under D flip-flops, here it is there, master slave D flip-flop. And you can get the pin configuration from this icon. Click on the module and get the pin configuration from here. 5th pin is the D input, 8th pin is the clock input, and Q is the 4th pin and Q dash is 1st pin. Now I'm on the Q pin, and you can add a clock using this input output palette. From this input output palette, you have a clock pulse generator. So to start the clock, click on this clock button, or click on this clock symbol, and start clock option is there in the top panel. Just start the clock. Now the clock was started. To change the input, just change on it and click on the clock again to run. So the clock is running and the bits are shifting accordingly for every clock pulse. To see the waveform, click on the show waveform button here. You can see the bit switch input and clock input and the outputs of the 4-bit displays you are seeing there on the screen. This way you can design your sequential circuits and you can simulate them. I'll give another 3 more minutes to complete it. I think we are running short of time. Implement it in as early as possible. Please go ahead. If you have any questions regarding this, please drop in the chat box. Where is MSD? See, in the right hand palette, you can see the sequential circuits tab. Under this tab, you go for the D flip-flop. There is a small arrow was there. You just click on. That will collapse and it will show a different types of D flip-flops. In that, go for the last one. Master slave D flip-flop. Any more questions, you can drop in chat box. Connect clearly in the sense. I think Yeah, I'm showing. I'm showing that. First it got disconnected. Yeah, if your bid display showing X means the component you have added is wrong. That module. Make sure that you added that master slave D flip flop. Just check it and let me know if you have achieved or not. see, if you have to run the clock pulse, to click on clock pulse every time. You need to click on the clock pulse and leave it. Okay.
Hello.
Yes, sir.
Hello.
Here, sir.
Hello.
Yes, sir. Yes, sir. I
Yeah.
can hear you.
So,
Sir, there is a question called how the simulator is different from Verilog to Verilog and VSDL.
yeah. So this is a tool with this kind of user interface through which they can do the design. So this also has certain features. For example, it can also generate Verilog code for modular design. So I hope you have shown them how to create a module from a design. Have you shown them how to create a module, labeling the pins and all that?
Yes, sir.
Yeah, that is important. So that it is a simulator. Now it has many other features which we can't cover now. So I'll refer one paper. Do you have the reference of that paper which was published for this work, Aditya?
Just a minute. It is in our page. So as of now, not with me, sir. I will share them.
Yeah, I'll send you the link. So you can send them that paper. So from that they can get to know more about the tool. So right now we will have to stop here more or less, isn't it? So
Yes, sir.
important thing is to show them how to create a module. Then they can use the modules to create their design. So that exercise which I gave them, they can then they will be able to do that exercise. All right.
Yes.
Okay. So there
And
are there are other features which possibly we can cover later on. All right. Yeah. Okay then. Yeah.
Okay, sir. It looks like we have covered all our questions. So, sir, should we head for a wrap up?
Did you head for your?
Wrap up? Should we end this
Yeah.
thing?
You can. So Aditya, have you completed your presentation? Whatever you wanted to present now?
yes, sir. Yes, sir.
Okay. I think then we can we can wrap it up now. Yeah.
Okay, great, sir. It's my request to all participants. I hope you have filled up the form which was provided to you all in the chat box for today's attendance. So, thank you, everyone. Thank you so much. Thank you, sir. We appreciate you all being here. Thanks again for joining us today, and we will see you next time. So with this, I end today's webinar. Thank you, sir. And Debojyoti sir, host, I will request you to end today's meeting.
Okay, ma'am. Okay.
Okay.
Okay then. All right. Yeah.